2162, Artem Abakumov.
Yeah, hello. I will share my screen right now.
Screen, please.
Hello, dear participants of the 12.
1 minute. Okay, please.
Full screen.
Okay, welcome.
Here we go. Hello, dear participants of 12th IEEE International Conference on Dependable Systems, Services and Technologies. My name is Artem Abakumov. First, I want to thank my colleague and co-author Vyacheslav Harchenko for inviting me as a speaker to this conference. And today we will talk on our current results on combining IMECA analysis and penetration testing to assess the cybersecurity of industrial robotic systems. During the speech, we will walk through motivation and states of the results, objectives of the research, discuss main results and possible case study in this area, and discuss some conclusions. Robots are going mainstream. All signs indicate that shortly robots will be everywhere as companions for older adults, manufacturing workers, healthcare attendants, etc. Many of these machines are self-propelled, so they must be secure, well-protected, and hard to hack. If not, instead of helpful resources, they could quickly become dangerous tools capable of wreaking havoc and causing substantive harm to their surroundings and the humans they are designed to serve. As we all know, we already experienced some consequences of substantial cybersecurity problems with the IoT devices that are impacting the internet, companies, and commerce. Cybersecurity problems in robots could have a much more significant impact. Incidents listed on this slide were accidents, but they demonstrate the potential serve consequences of robot malfunctions. A robot controlled remotely by attackers could cause similar incidents. With this in mind, we decided to review the architecture of industrial robotic systems and their set of probable vulnerabilities and potential attacks, and decided to develop a security and safety assessment method based on combination of IMECA analysis and penetration testing. Our object under study is a collaborative robot and its architecture, components, technologies, etc. Mechanically, a collaborative robot is an arm with two or more joints terminated by end effector. Cobots operate according to the task program. Here is on the diagram marked as. They are connected to their network via controller. We can imagine it as a box with a bunch of interconnected computers and other modules. This box controls the robot and includes human-robot interaction subsystems. The control system monitors and runs the robot mechanical parts and manages the interaction process between the robot, the environment, the operator, and services. It's important to note that a controller can work in automatic or manual mode. In automatic mode, it's designed for regular operations in production, but when the robot is in the manual mode, the operator can interact it using a special handheld device called touch pendant for programming and reprogramming processes. Usually, the controller connected to the SDK via internet also for programming purposes. Collaborative robots were designed for use in industrial facilities with limited access to them, and several built-in security mechanisms such as physical lock of the controller, safety settings modification checksum, HRI password protection, etc. But there are still some entry points usually exposed in the modern codes that attackers can use maliciously. They are dashed and all on this architecture. So the main thing we need to memorize from this slide is that key components of collaborative robots are task program, network, software development kit, external interfaces, and controller, which also includes access control system, firmware, and file system. Following the architecture of the cobot, we summarized recent studies and extracted from them common vulnerabilities for cobots. Let's list them now. Lack of integrity checks for configuration files. Cobot operates according to the configuration file loaded by the programmer using FTP or an API. However, in most cases, there is no security check to determine if the task program is secure, making it possible for attackers to inject malicious control commands to manipulate the cobot operation. Second one, weak integrity check of communication packets. The integrity check in the communication packets is unsophisticated, making it easy for attackers to manipulate communication packets in the manufacturing network. Clear text or weak encryption of transferred data. Due to traditionally deficient security awareness of robots, original equipment manufacturers, and the limited computing resources of the cobots, most communication data is in clear text or weakly encrypted, allowing attackers to parse the communication data and steal the robot's sensitive information. Weak credential storage encryption. Credentials are stored in the file with the weak encryption, allowing attackers to crack the file to obtain the credentials of all valid users. Default or hard-coded credentials. Some cobots have a default or hard-coded credentials which can be found in publicly accessible user manual or reverse-engineered firmware. Lack of preference configuration. The access control systems can be temporarily disabled when cobot boots, and most access control systems do not correctly configure access rights of different functions, allowing attackers with low privilege to manipulate critical functions of robots. Abused file read-written permissions. File systems of some industrial robots are exposed to the manufacturing network via services such as FTP, which risk the robot's files that store sensitive data being read or written by attackers without access rights. Lack of security checks. Some robots are equipped with publicly accessible SDKs to allow third-party development. However, the robots do not check the security of SDKs, allowing attackers to develop malicious software to manipulate the robots. Lack of firmware integrity check. The firmware images of the robot's control cabinet and touch pendant must be loaded when the robot boots. However, the robot does not check the integrity of the loaded firmware, allowing attackers to manipulate the firmware and thus the robot or touch pendant. And last, lack of physical security interfaces. If the attacker gets physical access to the controller, he can execute malicious payload on a locally connected USB device. We built a IDEF0A1 model of the proposed method. Since this scheme is a bit complicated, we will walk through only through the main stages. So, the main stages of proposed penetration testing method includes the next steps: information gathering, scanning, IMECA, attack, countermeasure selection, and reporting. The unique stage of the proposed method is analyzing cobot vulnerability criticality using IMECA technique. Potential vulnerabilities and occurrences in their occurrences in COBOT components are summarized in this table. For example, we evaluated the summarized list of vulnerabilities of COBOT's components using judgments from our own practical experience in the pen testing and analysis of available information about existing cases of attacks on COBOTs. The exploitation column separates into three subcolumns: probability, difficulty, and danger. The first subcolumn shows us advantage of using vulnerability to carry out an attack. The second column explains the complexity of using the vulnerability to conduct the attack. And the third column describes how dangerous a successful attack using the specified vulnerability can be. Each vulnerability row is rated using a low, average, high gradation for each cell of the exploitation subcolumns. The next step of IMECA technique is evaluating the type of effects, such as root case of the successful attack, occurrence probability, and effect severity of COBOT's components. The analysis shows that the most severe stands for operation manual attack mode. The operation manual attack mode can degrade manufacturing quality, efficiency, damage devices, or even cause injury of human operators by making the COBOT operate abnormally, which can be achieved by uploading malicious task programs, injecting malicious control commands, or changing the configuration area. Successful attacks may lead to violation of integrity, accessibility, or confidentiality. In context of penetration testing, such analysis helps us to determine which components and their potential vulnerabilities we need to take into account first, and which ones can be postponed due to the limitation of penetration testing. For example, time limits, fixed resource, or unavailability of some components for testing. Based on completed analysis, the most severe element is a task program and its related things: network, software development kit, and controllers access control system. A massive bunch of vulnerabilities of COBOT happen due to weak integrity checks at the different stages and poor authentication authorization mechanism. Malicious intrusions through these channels into task program flow may lead to certain scenarios like micro defects of end effector work results, unexpected COBOT shutdown and wake up, random robotic movement trajectory. Moreover, IMECA analysis help us to understand how efficient our penetration testing procedure is, and if it can be continuously integrated into the COBOT safety assessment flow. Vulnerabilities and the ways to exploit them can be reviewed after each successful attack process. Continuous IMECA analysis provides a transparent understanding of how heavily vulnerabilities and results of their exploitation affect the COBOT. In the presented work of combining the analytical risk-oriented method and experimental penetration testing method, we proposed a set of steps that can be applied to determine the security level of safety critical collaborative robot. Our further research should be carried out in the direction of experimental confirmation of the specified method on a real COBOT or its simulator. This process can be divided into stages that allow us to examine COBOT's components and comprehend results and draw more detailed conclusions. Thank you for your attention. I'm ready for some questions.
Thank you, Artem, for your presentation. And now we short time for questions. Any questions, please? Dr. Peter Popov, please.
Artem, I enjoyed very much your talk, really. excellent presentation, and the approach that you have taken is quite commendable. Can you go back to slide 11, please? No, not this one. Here, yes, this one. I think the last bullet point, which is shown here, is quite important. Cyber threats are not really staying static. I'm sure that you're perfectly aware of this. And it seems that this last bullet point, it will be quite interesting to consider conducting this at runtime, not to have it off the loop done by experts. I suspect that these numbers that are included here are done by experts, but do it somehow at runtime. So the question is whether there are plans to extend this work in this direction. And the second, if you're planning to do something like this, I'm quite keen to be involved if there is scope for other people than your co-author to work on this particular problem. Thank you.
Thank you for your question. I think we discussed with Vyacheslav this question. As a further steps, we can proceed maybe some questionnaire for experts that works in robotic systems sphere to understand if our current understanding of vulnerable places of cobot systems is true or not. Also, we want to confirm our results of our exploitation using maybe some cobot simulator. If not, if our results will not confirmed by this, we will think on what we can improve in our IMECA analysis to detect real vulnerabilities in the system. If it is, we will continue with researching the ways how IMECA analysis can be used after on the other steps of penetration testing, like exploitation. And we will use IMECA analysis during penetration testing as our point that we will rearrange each time we have new results that confirms vulnerabilities in the system or makes them false positives.
We would like to analyze robotic simulators to go ahead with this experience, and plus use real robotic system, but we understand limitation in this way. Thank you. Any other questions? No, thank you very much, Artem, for your presentation, and wish you